solving linear systems of 3 equations and 3 variables using row reduction. This is the part two of the series using matrices. So requirement to understand this part is to watch the part 1 of this video and go over the videos over matrices. So the first thing is that what we discussed that we can matrices are rectangular arrays of numbers, equations, variables, and the entire process of row reduction had nothing. If we kept a good bookkeeping, had nothing to do with the X, Y, Z variables when we were going through it. It just had to do with the coefficients that we experience. So the first step of doing the row reduction is actually converting the system into an augmented matrix. What is an augmented matrix? The definition is in your notes, but augmented matrix is the matrix of all the coefficients, and you put in 0 where a variable is missing, and attached to the vector or the n by 1 a matrix of the constants. So here, for example, the first row is going to be 3, 2, 5. And then 73. So let's write the matrix of the coefficients first. So I write 3, 2, 5. Then second row, 0, 7, 1. The third row, 2, 1, 5. Then I put this imaginary line that is just for bookkeeping for me. If I'm solving the system on a paper rather than using a machine, I want to have a method of bookkeeping so I can separate the matrix of coefficients from the matrix of constants. So then I'll put in the constants in there, 73, 50, and 60. And this becomes our augmented matrix. Things to notice. So beside putting in a 0 in here, and beside in anywhere that the variable is missing, a term with with that variable is missing, you put in a 0. You put in all the coefficients that in one side, and then you put all the constants on the other side. To be able to write augmented matrix, we really have to have the constants on the other side of the equations every time. So what's the next step? The next step is pretty much the same as doing the same process for systems. Things to notice, this time when you're talking about leading coefficient, you're really talking about a non-zero term in that row, rather than when you were doing the leading coefficient in here, or a leading term in a system, we were talking about the first one over here. It implicitly contained the fact that all the leading, if this is the first non-zero leading coefficient, because we could have assumed this is a term with a 0 coefficient in here. So now everything else works the same. Leading ones are similar definitions as they are for the systems. We want to have indent. Indent this time, instead of an empty space, we'll have a 0 in it. For example, from row 1 to row 2 indent exists over here as well, because then the next non-zero coefficient is indented in. Now, what is the process? The first part of it is the creating one in the first row. We're lucky enough that the first entry in the first row is non-zero. Therefore, I use the row operation number 1 to create a leading one. How's that work? That is R1 times divided by 1/3 goes back to R1. Again, as we did with the systems, every element, every entry in the first row has to be multiplied by 1/3 or divided by 1/3. So I write it like this: 3 divided by 3 makes it 1, 2 divided by 3 makes it 2/3, 5 divided by 3 makes it 5/3, 73 divided by 3 makes it 73 divided by 3. And all the other rows stay the same. So what's the next step? Now that I have a leading one in here, I want to create zeros. So instead of eliminating the terms underneath, now I'm creating zeros underneath a leading one. I was lucky, and the second row had a leading had a 0 underneath leading one. So what I need to do is to create a 0 in the row 3 underneath leading one. How does that work? Again, they're using the third operation in this list. So what I do is row 3 plus -2, because this is 2, -2 times row 1 goes back to row 3. So it's row 3 plus -2, row 1 goes back to row 3. Again, what I want to do, if I want to use a multiple of a row, so that I make this entry 0. And so the row that I'm using is the row with the leading one that is above that 2. And then I continue. So this is going to be, let's write it on a scratch paper. So row 3, which is 2, 1, 5, and 60, and -2 times row 1, and we add it up to get 0, -1/3, 5/3, and 43 divided by 3. Now, rewrite the matrix. Row 1 is not changing. See, the only row that is changing is row 3. And so 0, 7, 1, 50, and row 3 is this one. So this arrow going to row 3 means that the only row that is changing is row 3. The next step is, now I have a leading one, zeros underneath it, is to create another leading one. And I'm lucky enough that this was just one indented, so I'll take row 2 and I divide by the coefficient, by leading coefficient in there, and I create a leading one right there because it's already indented. So here is going to be row 2 times 1/7 goes to row 2, and the matrix will look like this. Row 2 is the only one changing, so I rewrite. The first row and the third row. And then I divide every entry in row 2 by 7. 7 divided by 7, 1 divided by 7, and this was 50 divided by 7. The next step, now I have one leading 1, zeros underneath, another leading 1, and there is a non-zero entry underneath. So the next step would be to actually create a 0 underneath that leading 1. So going back in here, how do I create a 0 underneath the leading 1? I'm using the third row operation, and third row operation tells me to multiply the corresponding row with the leading 1 by negative 1/3, negative of this, and then add it to the third row. So it becomes row 3 plus 1/3. Row 2 goes back to row 3. So row 3 is negative 1/3, 5/3, sorry, 0, negative 1/3, 5/3, 43/3, 1/3 times this row, 1/3, 1/21, 50/21, and then we add them together and we get 0, 0, 36/21 and 288/21. Now let's replace everything. What we have here is the first row doesn't change. Second row doesn't change. Third row is changed into this row. Okay, so leading 1, 0 underneath, leading 1, 0 underneath. There is a possibility of getting another leading 1. How do we do that? The way to do this is that actually this is a guaranteed leading 1 in this case. But what we do is, as usual, it's indented. What you need to do is to divide by this coefficient. So row 3 multiply by the reciprocal of that goes back to row 3. If you calculate, it would be 288 divided by 28 times 21 times 21 divided by 36, which is going to give you 8. So the last row, first one the same, second one the same, third one is going to be 0. This becomes 1. This becomes 8. So now, leading 1, leading 1, leading 1, and I know because they're indented. Zeros underneath all the leading ones. In here, that's the last leading 1. There's nothing underneath it, so we're all good. So this gives me what I call this is the row echelon form. Row echelon form, or REF. What do we do with row echelon form? What you do is you take this, you rewrite a system of equations where, remember, method of bookkeeping, this is the matrix of coefficients and this is the constant matrix. And then you use the back substitution to solve. Now, let's write that down. And so another thing, as we did with systems of equations, every time we did some row operation, we called the new system and the row equivalent system. Here, every time we do row operations, these matrices are going to be the row equivalent matrices. So, and that means that the system associated with this is going to give you the same solution as the system associated with the first augmented matrix, which is that. So rewrite this one times. Remember, this is the column that associates with X. This is the column associating with Y, Z, and that's the constant. So it gives me 1 times X plus 2/3 of Y plus 5/3 of Z equal to 73/3. This row gives me 0 times X, Y plus 1/7 Z equal to 50 divided by 7. Third one, X plus 0 times X plus 0 times Y is 0. Z equal to 8. So if you go back to the videos, you see that the last step that we did, that was the system was in the row reduced form. It was in the row echelon form, was exactly the system. The process from now on is easy to do. Z is already solved. What you do is you replace it in here, then you solve for Y, which gives you Y plus 8/7 equal to 57, and Y is equal to 6. Then you use these two, back substitute in here, and then you get X plus 2/3 of 6 plus 5/3 of 8 equal to 73/3, and X solves to be 7. And then the answer is 7, 6, 8. So I recommend going back to the video on this, the first part of this video, that we use systems, and comparing it to this part to see how everything makes sense. And that's it for today.